Hello everyone, my name is Leonardo and I'm going to present the article entitled Detection of Knocking Combustion using Continuous Wavelet Transformation in a Convolutional Neural Network. Basically, I'm going to expose the combustion engines, about the problem that we are going to have, the proposed approach, dataset and labeling, method presented, some results and the conclusion. Normally, in combustion engines works in a four-stroke stages. So basically, the first stage is to get the mixture of air and fuel injected inside of the cylinder. After that, the piston goes up to have the compression, and in the third part is the combustion, which is caused by the spark plug. And after that, normally it should, and in the third part is the combustion, which is caused by the spark plug. And after that, normally it should burn all the fuel inside of the cylinder, but that's not always what happens. It may, under different circumstances, it may generate an important topic that we are going to expose today, which is the engine knock. Normally, the engine knock happens when portion of the fuel inside the cylinder detonates before the rest of the fuel, as is presented in the figure presented here. So, the engine knock can be caused by some problems, which is the low octanage of the fuel, bad timing of the crankshaft, the lean air and fuel mixture, or even a high temperature of the environment. The symptoms are normally the knocking or pinning noise, but we can get that the engine knock is happening when we have a higher CO2 emission or even a lower fuel economy. So normally the engine knock uses conventional methods to identify if it's happening. In this case, they use the threshold value exceeded to understand if the event has occurred. To do that, we need to calibrate the threshold for each engine. The proposed approach of this article is to detect the knocking combustion in three different internal combustion engines and validate with the specialist of this phenomenon to identify if the detection was right or not. We are going to use a continuous wavelet transformation. So inside of this the cylinder, we are going to get the sensor of pressure in time frequency domain. That is going to lead us to the coefficients. And after that, we're gonna put this coefficient in the convolutional neural network to extract this feature and then detect if in that event occurred or not the event of knocking. We are going to use a single cylinder in a 4-stroke SI gas engine, and we are going to get the pressure with a piezoelectric. We're going to have different characteristics. So in the end, we are going to do that to have a better generalization of the model. The engine speed is going to be of 1500 revolutions per minute. Spinning rate is going to be 0.1 crank angle, and we're going to get 7200 per cycle. So, as I told before, each of the engines has its own characteristics, and we are going to start identifying for each of the engines the occurrence of the knocking or no knocking. So we can see in the first image that we don't have knock for the first engine, so we can see here that this curve keeps steady. But when we have a knocking occurrence, we can see from 10 to 20 that the values are starting to get messy. And this happens to the second series too. In the no knocking, it keeps kind of steady, but when we have a knock, we have the oscillation of the pressure. And the third one, we have the same thing. Basically, we are going to extract this data from the engine, and then in the end, we are going to verify with the specialist that has experience in this area, so they can detect if in a time frame has knocking or no knocking. For example, we are going to slice part of the data of the signal from 5 degrees to 35, which has the bigger part of the oscillation. So from 7,200, we are going to get just 300 points for each cycle. First, we are going to slice the data. After that, we are going to put the result on the continuous wavelet transformation. After that, we are going to get the coefficients to put in the CNN classifier. And then in the end, we are going to get the occurrence or not of the knocking. The continuous wavelet transformation has numerals families, which we are going to use some of them in this experiment. In this image here, we can present the architecture of the CNN. We are going to have the shape of 300 as we split the data before, and we are going to use the optimizer atom. So we can see that here is the input that we are going to put in the CNN that comes from the wavelet transformation, and in the end we are going to have the dance response that we are going to get from knocking or non-knocking signal, the coefficient. And to do that, we are going to use the wavelet function, which is called the Gaussian, and we are going to look through the data from a range to 1 of 500. If we can see here of the difference about no knocking and knocking, most of them until 100 are similar for each cases, but after 100 we can see that the data starts to get different from the knocking and no knocking one. So we are going to use the maximum scale of 100. Defining the function wavelet plus the maximum scale, we can plot the scalegram of this data. Plot the scalegram here, and we can see here on the series 2 that in the no knocking one, we can see here that's kind of simple here, but in this area here we can see that we have an disturbance, which it's about from 3 kilohertz until almost 20 kilohertz. In this part here, we can see the architecture of the CNN, which we have 20 epochs, batch size of 32, depletion of 2 epochs, waiting for the test loss value to be reached, in the learning rate. About the results, we can see here that we have the proposed approach and the threshold value approach. We can see here that the result of the test is higher than the result of the threshold value. Generalize the dataset, mixing, train, and test to verify if it's possible to don't be necessary to use different engines to train the data set. We can see that the proposed one is trained better, but the test part is not so good. 69% of the specialists agree with the proposed approach. We can analyze here from each wavelet family that the Gaussian and the Moore have pretty much the same value for training, but for testing the Gaussian one is better than the Moore. To conclude this, we understand that a better understanding and handling of this phenomenon significantly reduces the CO2 emission, and the classification with the proposed approach has an increase of 6.50%. But they present here that the calibration is not mandatory, but we saw that generalization proposed is not that good. So basically that's it. If you guys have some questions, I'm open to answer them. Thank you.